Welcome back to Fun Facts Online. Have you looked up at the night sky lately? You might have noticed that the celestial tapestry is no longer purely the domain of stars, planets, and the occasional passing comet. Instead, the steady rhythmic march of artificial satellites, often moving in bright, linear trains shortly after launch, has become a permanent fixture of the twilight hours. We are firmly entrenched in the era of the satellite megaconstellation. For the billions of people who will receive high-speed, low-latency internet access from the most remote corners of the globe, this is a massive triumph of modern engineering. Yet, hidden miles above the Earth's surface, a silent and invisible environmental crisis is unfolding. Today, we are going to dive deep into exactly what is happening in our upper atmosphere, the unexpected consequences of spaceflight, and why the sky quite literally has a limit. Let us start by talking about the architecture of the sky. To understand why spacecraft emissions are so uniquely dangerous, we have to look at how our atmosphere is layered. We live in the troposphere. This is the dense, weather-rich layer extending from the surface up to about 10 kilometers, or roughly 6 miles high. In the troposphere, pollution is relatively short-lived. Rain, wind, and convection currents act as a planetary washing machine. They scrub soot, smog, and aerosols from the air within days or weeks. But above the troposphere lies the stratosphere, extending from roughly 10 to 50 kilometers above the surface. The stratosphere behaves entirely differently from the air we breathe down here. It is characterized by something called a temperature inversion. Unlike the troposphere, where it gets colder the higher you go, in the stratosphere, the air actually gets warmer with altitude. This happens largely because the ozone layer, which resides here, absorbs ultraviolet radiation from the sun. Because warm air sits on top of cold air, the stratosphere is highly stratified, which is exactly where it gets its name. It is profoundly stable. There is no rain, there is no weather, and there is virtually no vertical mixing. When pollutants are injected into the stratosphere, they do not just wash away. They become trapped, lingering for years. In this pristine environment, even microscopic quantities of aerosols can exert an outsized influence on the global climate and atmospheric chemistry. And unfortunately, it is within this delicate vault that rockets deliver their payloads, and it is here that the remnants of dead satellites come to rest. Let us examine the very beginning of a spacecraft's life cycle. It starts with a violent, fiery ascent. For decades, the environmental impact of spaceflight was considered negligible. It was just a statistical rounding error compared to the immense greenhouse gas emissions of terrestrial aviation, agriculture, and heavy industry. Humanity was only launching a handful of rockets each year. But the math is changing rapidly. As the commercial space industry targets launch cadences of multiple rockets per week, the equation shifts. Rockets are the only human-made pollution source that injects combustion products directly into all layers of the atmosphere, from the troposphere right through the stratosphere, the mesosphere, and into the thermosphere. The chemical footprint of a rocket launch depends entirely on its propellant, and the truth is, none of them are completely benign. Take, for example, many of today's workhorse orbital launch vehicles, like SpaceX's Falcon 9. They rely on a highly refined form of kerosene known as RP-1, which is burned with liquid oxygen. The combustion of RP-1 produces vast quantities of black carbon, which we commonly know as soot. Now you might be thinking, commercial airplanes produce soot too. But commercial aviation cruises at the very bottom of the stratosphere, or the top of the troposphere. Rockets, by contrast, leave a continuous vertical plume of black carbon through the entire stratosphere. Particle for particle, black carbon injected by rockets in the upper atmosphere is nearly 500 times more efficient at warming the Earth than soot from surface or aviation sources. This is because stratospheric black carbon absorbs incoming solar radiation, heating the surrounding upper atmosphere while simultaneously cooling the Earth's surface. This process creates an overall positive radiative forcing, meaning it acts like a thermal blanket and causes climate warming. Then we have other launch systems that rely heavily on solid rocket motors. When solid propellants burn, they emit a heavily destructive cocktail of chlorine gas and aluminum oxide particles, also known as alumina. Chlorine is a highly efficient ozone-depleting substance. In the stratosphere, a single chlorine atom can destroy up to 100,000 ozone molecules through a catalytic cycle, before it is finally neutralized. Compounding this severe damage, the alumina particles expelled by solid rocket motors provide an ideal surface area for these chemical reactions to take place. The alumina essentially acts as a catalyst, supercharging the chlorine-based chemistry that strips away the ozone layer. Furthermore, unlike highly reflective sulfur aerosols that actually cool the Earth, the alumina particles emitted by rockets have been found to absorb upwelling long-wave terrestrial radiation. This results in a net positive radiative forcing, further warming the climate. Now, let us talk about the paradigm shift in how we use space. Historically, those few satellites we launched each year were massive, incredibly expensive, and designed to operate in high orbits for decades. Today, companies like SpaceX with Starlink, Eutelsat with OneWeb, and Amazon with Project Kuiper are building what we call megaconstellations. These consist of thousands to tens of thousands of satellites operating in low Earth orbit. To provide low-latency broadband internet, these satellites must orbit very close to the Earth. Because low Earth orbit features a slight atmospheric drag, satellites here require constant station keeping. And eventually they reach the end of their operational lives, which for these cheaper mass-produced satellites is only about 5 years. This brings us to a major paradox in space sustainability. To prevent the dreaded Kessler syndrome, which is a theoretical scenario where space debris continuously collides, creating an impassable cloud of shrapnel that could lock humanity on Earth forever, regulations require that these low Earth orbit satellites be safely disposed of. But disposal in this context means intentionally deorbiting them so they burn up in the atmosphere. With the number of low Earth orbit satellites projected to grow from around 5,500 in 2022 to potentially over 60,000 by 2040, we are facing an era where an obsolete satellite will plunge into the atmosphere every single day. This creates a massive, continuous influx of human-made material. Researchers calculate that the mass of artificial spacecraft re-entering the atmosphere is rapidly approaching and will soon exceed the natural influx of cosmic dust and meteoroids that have bombarded Earth for billions of years. So what exactly happens when a 250-kilogram satellite hits the mesosphere, the layer just above the stratosphere, at 27,000 kilometers per hour? It does not simply disappear into nothingness. The intense kinetic friction of re-entry generates extreme heat. This causes the spacecraft's metallic hull, solar panels, and internal electronics to melt and ablate. The satellite is entirely vaporized into superheated gases. As these gases cool in the upper atmosphere, they condense into metallic nanoparticles. These are primarily aluminum oxides, but they also form a complex alloyed mixture of other metals. Because these particles are microscopic, they do not fall quickly out of the sky. Gravity pulls them down at an agonizingly slow pace. It can take up to 30 years for the byproducts of a single vaporized satellite to settle from the top of the mesosphere down into the stratospheric ozone layer. For years, the atmospheric fate of these vaporized spacecraft was purely theoretical, but recent high-altitude scientific missions have provided startling empirical proof of this metallic rain. Let me tell you about the SABRE mission in 2023. NOAA scientists flew a specialized high-altitude research aircraft deep into the Arctic stratosphere. Utilizing a custom-built instrument called the particle analysis by laser mass spectrometry, they analyzed the chemical fingerprint of individual stratospheric aerosols. What they found was truly unprecedented. The researchers discovered that 10% of the sulfuric acid particles in the stratosphere currently contain traces of metals originating exclusively from vaporized spacecraft. They detected over 20 distinct elements, including lithium, aluminum, copper, lead, beryllium, and zinc. Crucially, they found elements that simply do not occur naturally in meteoric dust, such as niobium and hafnium, which are highly refined metals used in superalloys for rocket engine nozzles. They also found silver, which is a clear marker for melted satellite electronics. The ratios of these metals perfectly match the alloys used in aerospace engineering. This definitively linked stratospheric pollution directly to the space industry for the very first time. And if we look ahead to 2040, as the deorbiting of megaconstellations reaches its peak, scientists estimate that up to 50% of all stratospheric aerosols will be contaminated with these spacecraft metals. Ground-based technologies are now detecting these distinct chemical signatures immediately following re-entry events too. In early 2026, atmospheric physicists operating a resonance fluorescence LiDAR in northern Germany detected a massive, invisible cloud of lithium atoms hovering in the mesosphere at an altitude of 96 kilometers. The spike in lithium, a metal rarely found in natural cosmic dust, was recorded just 20 hours after the uncontrolled re-entry of a SpaceX Falcon 9 rocket stage over Europe. The rocket's aluminum-lithium alloy hull had dumped approximately 30 kilograms of vaporized lithium into the upper atmosphere. This caused a localized atmospheric spike, 10 times the natural background level. We are conducting a massive, uncontrolled chemistry experiment in the most fragile layer of our atmosphere. This introduction of vast quantities of aluminum, lithium, and copper into the stratosphere is a severe threat to the ozone layer. Remember, the ozone layer is what protects all terrestrial life from deadly ultraviolet solar radiation. A typical 250 kilogram megaconstellation satellite can generate around 30 kilograms of aluminum oxide nanoparticles during its demise. If projections hold true, the routine replacement of satellite megaconstellations could inject upwards of 360 to 10,000 metric tons of aluminum oxides into the upper atmosphere every single year. Aluminum oxide is a known catalyst for ozone destruction. When these nanoparticles settle into the stratosphere at an altitude of about 40 kilometers, they alter the local chemistry, strongly promoting the activation of chlorine. Once activated, chlorine shreds ozone molecules. Think about the incredible global effort of the 1987 Montreal Protocol. Back in the 1980s, the world realized that everyday products like hairspray and refrigerants were releasing chlorofluorocarbons that were tearing a hole in the ozone layer over Antarctica. The global community came together to ban those chemicals, and the ozone layer slowly began to heal. Decades of that painstaking global cooperation could be significantly undermined by the unregulated injection of space debris alumina. Furthermore, the introduction of novel metallic elements affects the formation of polar stratospheric clouds. During the dark, freezing polar winters, trace amounts of water vapor and nitric acid freeze around aerosol particles to form these clouds. These clouds act as massive chemical processing plants. Their icy surfaces accelerate the conversion of benign chlorine compounds into ozone-destroying radicals. Research indicates that metals from spacecraft act as highly efficient ice nuclei. This means they could potentially increase the frequency and density of polar stratospheric clouds, thereby supercharging ozone depletion over the Earth's poles. But the threat goes beyond ozone depletion. The continuous deposition of satellite debris promises to alter the fundamental thermal dynamics of the Earth's upper atmosphere. A landmark 2025 study led by researchers at NOAA's Chemical Sciences Laboratory modeled the impact of 10,000 metric tons of alumina continuously deposited by falling low Earth orbit satellites. The models revealed shocking potential climate anomalies. The accumulation of these metallic aerosols absorbs and scatters radiation, creating localized temperature variations. The study found that this specific volume of alumina could heat up sections of the mesosphere by as much as 1.5 degrees Celsius. Even more alarmingly, the localized heating in the upper atmosphere is projected to alter the speed and circulation patterns of the polar vortex. The polar vortex is the massive swirl of freezing air that dictates winter weather patterns across the northern hemisphere. We are effectively conducting unintentional geoengineering. In fact, some scientists have drawn direct parallels between satellite re-entry pollution and stratospheric aerosol injection, a controversial climate engineering proposal to artificially cool the Earth by spraying reflective particles into the sky. While that intentional geoengineering aims to reflect sunlight, spacecraft debris consists of different materials whose radiative, chemical, and thermal properties are highly unpredictable and currently completely uncontrolled. Despite this mounting scientific evidence, the environmental impact of spaceflight on the Earth's upper atmosphere remains largely unregulated. Current international space law is anchored by the 1967 Outer Space Treaty. It mandates that countries are liable for direct physical damage caused by their space objects, for instance, if a piece of satellite debris miraculously survives re-entry and crashes into a house. However, these treaties were written in an era when space was entirely the domain of sovereign governments, and the idea of launching 60,000 commercial satellites was pure science fiction. There is currently no unified framework holding corporations liable for cumulative invisible chemical damage to the stratosphere. So, how do we govern the sky? Legal scholars and environmental policy experts are beginning to seek solutions outside traditional space law. A 2025 analysis published in Environment Science and Policy for Sustainable Development argued persuasively that the Vienna Convention and the Montreal Protocol actually offer the ideal legal frameworks to govern stratospheric aerosols emitted by rockets and re-entering satellites. Because the Montreal Protocol has a proven track record, a science-based precautionary approach, and a direct mandate to protect the ozone layer, it could be adapted, either through a protocol amendment or non-binding guidance, to regulate the commercial space industry's emissions. To preserve access to space while protecting the Earth, the aerospace industry must pivot. We need to look toward design for demise protocols that account for chemical outcomes, not just physical ones. Currently, satellites are engineered to guarantee that their components physically melt completely during re-entry, to avoid injuring people on the ground. Moving forward, materials science must focus on utilizing alloys and composites that do not catalyze ozone depletion or cause significant radiative forcing upon vaporization. Additionally, the propulsion sector must continue its shift away from solid rocket motors and heavily polluting kerosenes. We need to look toward cleaner alternatives like liquid methane or liquid hydrogen. While these still emit water vapor and some nitrogen oxides, they eliminate the catastrophic black carbon and alumina footprints that are doing so much damage. The space age has brought humanity immeasurable benefits. The new wave of satellite megaconstellations promises to bridge the digital divide, connect remote communities, and revolutionize global telecommunications. But this progress must not come at the expense of the very atmospheric shield that makes life on Earth possible. For too long, we have treated the upper atmosphere as an infinite, empty void, a vast cosmic trash can capable of absorbing limitless amounts of exhaust and debris. The discovery of lithium clouds, the detection of niobium and hafnium in stratospheric aerosols, and the stark climate models predicting altered polar vortexes all point to a singular truth. The sky has a limit. As we push further into the final frontier, we must recognize that space exploration does not begin in the vacuum of orbit. It begins and ends right here in our atmosphere. Ensuring the sustainability of space means ensuring the sustainability of the skies above our heads. If we fail to recognize the environmental impact of our spacecraft, we risk trading the protection of the ozone layer for the convenience of global broadband. And that is a price far too steep for future generations to pay. Thank you for joining me on this deep dive. Stay curious, keep looking up, but never forget to think about what is happening right between us and the stars. See you next time on G Fun Facts Online.